Now we transition from the general introduction to the first main content block: water properties, crude oil properties, and fluid saturation. From here onward, we focus on practical reservoir engineering quantities you will see repeatedly in calculations, reservoir simulation, and field reports. Every oil and gas reservoir has water associated with it, usually as formation brine. In reservoir engineering, we describe water using three core properties: water formation volume factor, VW, which relates one stock tank barrel of water at surface conditions to its volume at reservoir conditions; water compressibility, CW, which is usually small because water is only slightly compressible; water viscosity, μW, which controls flow resistance and is measured in the lab using a viscometer. Also, engineers must always consider produced water because it affects facility design, corrosion, scaling, and operating costs. Crude oil is a complex mixture of hydrocarbon molecules. As reservoir engineers, we usually focus on bulk properties that affect reservoir flow and surface processing. These properties, like oil formation volume factor, oil compressibility, viscosity, and gas-oil ratio behavior, are measured in the PVT cell under controlled pressure and temperature. The key teaching point here is, crude oil properties are not constant numbers, they change strongly with pressure and temperature. Now we move to fluid saturation, which is one of the most fundamental reservoir concepts. Saturation is the fraction of pore volume occupied by a given fluid. We define SO equals VO/VP for oil saturation, SW equals VW/VP for water saturation, SG equals VG/VP for gas saturation. Saturation is an intensive property and is always defined with respect to the pore volume. In practice, we must specify the pressure and temperature conditions under which these volumes are measured. Reservoir conditions and laboratory conditions can differ. This slide highlights a key mathematical relationship. Pore volume is shared by fluids, so saturations must add up for oil-water systems. So plus SW equals 1 for three-phase systems. So plus SW plus SG equals 1. This means not all saturations are independent. In two-phase flow, only one saturation is independent. In three-phase flow, only two are independent. This is crucial in simulation and interpretation. When one fluid increases, another must decrease. This slide emphasizes that pore volume contains fluids and therefore mass is distributed among water, oil, and gas. At laboratory conditions, gas density is sometimes treated as negligible compared to liquids for some measurements, but in reservoir conditions gas density can be important. The key takeaway point: always be careful about conditions and assumptions when converting between mass, volume, and saturation. This slide tells the petroleum accumulation story. Initially, reservoir pores are saturated with water. Then hydrocarbons migrate into traps because they are less dense than water and buoyancy drives them upward. As oil and gas accumulate, fluids distribute themselves so that gravity and capillary forces reach equilibrium. Importantly, even in the hydrocarbon zone, some water remains as a minimum water saturation, often called irreducible water saturation in water-wet systems. This explains why pure oil saturation is not realistic in real reservoirs. There are two broad ways to determine saturations: direct methods, mainly core analysis, indirect methods, such as capillary pressure measurements and well log interpretation. Core gives direct rock and fluid evidence but is sparse and can be disturbed by drilling. Logs are continuous but indirect. In practice, the best evaluation combines core plus logs plus capillary concepts. Core saturations can be affected by drilling. When drilling is overbalanced, drilling fluid filtrate can invade and flush the core. Depending on mud type, the invading filtrate may be water-based, oil-based, or even gas/foam related. This matters because it can change the measured saturations compared to true in situ reservoir saturations. This slide is a key warning. Core saturation is valuable, but interpretation must consider drilling conditions. As core is brought from bottom hole conditions to the surface, pressure and temperature change drastically. Gas can expand and escape, fluids can redistribute, water may move, and some oil may be lost. This is why preserving core and correcting for these effects is so important. The teaching point: when you see core SW, always ask what corrections or assumptions were applied. This slide explains how core saturations are used in practice. With water-based mud, core saturations may help identify the presence of an oil zone and estimate original contacts. With oil-based mud, minimum interstitial water saturation may be more accurate. Core saturation information also helps calibrate indirect methods such as log interpretation and capillary pressure-based saturation models. This slide is typically used to show how saturation varies with depth and how the transition between oil-bearing and water-bearing zones can be inferred. The key messages: contacts like OWC and GOC are not always sharp. Capillary effects and rock quality create transition zones, and core saturation profiles can help identify those transitions. This is a very practical reservoir engineering slide. It highlights that reservoirs can still be productive even when water saturation is relatively high, especially in low permeability rocks. In tight formations, hydrocarbon production can occur with SW values that might seem too high if you only think in simplified terms. The key lesson: producibility depends on permeability, relative permeability, and saturation, not saturation alone. This slide introduces two common lab methods for saturation determination: a retort distillation, solvent extraction. Each method has advantages and disadvantages, and the best choice depends on rock type, required accuracy, time, and whether the core must be preserved. This slide shows the retort setup. The idea is to heat the core so fluids are vaporized and collected, allowing measurement of recovered oil and water volumes. It is fast and direct, but the temperature conditions are harsh and can damage both the sample and the fluid composition. Retort is fast, often less than an hour, and it provides direct measurement of both oil and water volumes recovered. For many operational workflows, that speed is valuable. This is why retort is often used when rapid results are needed. Retort has serious disadvantages. It uses very high temperatures, which destroy the core sample. Water of crystallization in clays can vaporize and falsely inflate measured water. Oil can crack into lighter components that do not recondense, and coking can produce carbon residue. The key lesson: retort is fast, but it can introduce bias and cannot preserve the sample for future measurements. This slide highlights that clays contain bound water that can be released at high temperature, creating measurement errors. For clay-rich formations, retort may overestimate water saturation unless corrections are applied. This is why understanding mineralogy is part of proper core saturation interpretation. Here the message is: at high temperature, crude oil composition can change. Cracking breaks long hydrocarbons into smaller ones, and coking leaves carbon residue. Both effects can distort saturation measurements. This is an excellent slide to teach students that measurement method matters as much as the measurement itself. This slide typically explains how recovered volumes are converted into saturations using pore volume. Emphasize the workflow, measure total fluid volumes recovered, estimate pore volume, and compute SW and so. Also remind students that corrections may be necessary for clay-bound water and lost volatiles. Solvent extraction uses solvents to remove fluids from the core without destructive heating. This method can be integrated with core cleaning workflows and is often preferred when preserving the sample is important. Solvent extraction can provide accurate water saturation and is non-destructive, meaning the core can still be used for later tests such as permeability, capillary pressure, and relative permeability. It can also be cost-effective if incorporated into routine cleaning. The disadvantages are that it is slow, it can take days, and oil volume is not measured directly because oil remains in the solvent mixture. So solvent extraction is higher quality for some outcomes but slower and requires careful handling in calculation. This slide presents calculation logic for converting extracted water mass/volume into saturation. Emphasize careful unit handling and the need for reliable pore volume measurement. Also mention that in practice, labs follow standardized protocols to ensure reproducibility.